Here is the fourth behavioral design pattern from the famous Gang of Four design patterns book. This one is called Iterator Pattern, and it is a pattern you use when you want to access the elements of a collection sequentially without exposing its underlying representation. I will start with a quick summary of what we are trying to accomplish with this pattern. The iterator pattern is a good choice when you are trying to accomplish the following. You have a collection of elements. You want to sequentially access each element from start to finish. You want to hide the underlying representation of the collection. Let's go through the points one by one. So, to start, we need to have a collection of elements. This can be a simple data structure, like a list or array. But it can also be another design pattern, like the composite pattern. The key concept is that the collection has one or more elements, a start and a finish, and we want to sequentially access each element. Most built-in data structures, like the array and the list, already provide support for iteration. We only need this pattern to enable iteration on data structures that do not support it out of the box. The iterator pattern offers a number of benefits. The most obvious benefit is that the pattern provides iteration for data structures that themselves do not provide it. With the pattern in place, you can step through the data structure just as if it were any other collection or list. The pattern also lets you define more than one type of iterator. For example, in a tree data structure, you could implement both breadth first and depth first iterators with this pattern, without polluting the data structure with methods for the different kinds of traversal. The pattern also provides for more than one pending traversal on the same list. This allows you to use the iterator pattern in scenarios where multiple threads need to access elements in the same shared collection. And finally, the pattern provides a uniform interface for traversing many types of element objects. This saves you from having to build distinct iterators for every possible data type. Here is the UML diagram of the iterator pattern. So here's how the pattern works. We have some kind of aggregate class in our code that contains a collection of elements that we want to sequentially access. The collection class is called concrete aggregate in this diagram, and you can find it on the left of the middle in the picture. The concrete aggregate class is derived from an abstract base class called aggregate that sets up the iterator pattern interface. The base class defines a method called createIterator, and the derived concrete aggregate class implements the method. The createIterator method returns a new iterator instance. This is a specialized class for sequentially accessing each element in the collection. We can find the interface of the iterator class in the top right of the diagram, in the abstract Iterator class. This class defines 4 members for accessing the elements in the collection. First, for resetting the iterator to the first element in the collection. Next, for moving the iterator to the next element in the collection. Is done, for detecting if we have reached the final element in the collection. And current item, for retrieving the current element. With these 4 members, a client can sequentially access each element in the collection. A client starts by calling first to move the iterator to the first item in the collection. Then, for as long as the isDone member is false, the client reads the current item field and calls next to move the iterator to the next element. You can see in the diagram that the abstract iterator base class defines the interface, and there can be many concrete implementations of the iterator. One implementation, called concrete iterator, is shown in the diagram. This is the class that is returned when you call the createIterator method on the concrete aggregate class. The .NET framework has a specific implementation of the iterator pattern that is pervasive throughout the entire base class library. Each collection class implements a special interface called IEnumerable. This is the equivalent of the aggregate base class in the iterator pattern. The interface allows you to create an iterator for the collection. Iterators in .NET also have a special name. They are called enumerators. And so, the method to create one is not called createIterator, but getEnumerator. Enumerators in .NET use an interface instead of an abstract base class. And it provides the following fields for sequentially accessing elements in a collection. Move next, for moving the iterator to the next element. This also moves an initialized iterator to the first element, and the method returns false if there are no more elements available in the collection. And current, for retrieving the current element. With these 2 members, a client can sequentially access each element in the collection. A client starts by calling moveNext to move the iterator to the first item in the collection. The method will return false if the collection is empty. If the method returns true, the client will keep reading the current field and calling the moveNext method until the method returns false. You can see that the .NET implementation of the iterator interface is slightly more compact, using only 2 fields to achieve the same result. When you use the forEach keyword in C#, the process that I just described is exactly what happens behind the scenes. The C# compiler does all the heavy lifting for you by creating a new enumerator instance and setting up a loop to sequentially call the moveNext method and read the current field to access all elements in the collection. Okay, I am going to implement a very simple iterator with the following classes. Let's take a look at the code. I will start with the concrete aggregate class, called myCollection in my example. You can see that it is a simple class with 3 protected fields, called field A, field B, and field C, and a constructor for initializing these 3 fields. I am going to create an enumerator so that I can use the for each keyword to sequentially step through these 3 fields. So the first step is to implement the IEnumerable interface. You can see up here in the class definition that I implement the interface. And down here is the getEnumerator method, which returns a new instance of the myCollection enumerator. And here is the myCollection enumerator class. You can see that it implements IEnumerator. The implemented interface members are down here. I use a simple integer state value to step through the 3 fields, and I use a switch statement in the current property to return the correct value. Now that both the IEnumerable and IEnumerator interfaces are implemented, I can access the collection with the for each statement. Check out this code here in the main program method. I use a for each loop to directly access the fields in the myCollection class, just as if this were a regular collection class. Okay, let me run the program to prove that everything is working. I am compiling the code now. And I'm running the code now. And there you go. All 3 field values appear on the console. Everything works. Here is a quick checklist you can use. First, implement the IEnumerable interface on the collection class. Then design an enumerator class that implements the IEnumerator interface. Have the IEnumerable.getEnumerator method return a new enumerator instance. And finally, have clients use a for each loop to sequentially access each element in the collection. And here are some final comments. By combining the composite pattern with the Iterator pattern, you add iteration support to a tree data structure. The interpreter pattern uses a data structure very similar to the composite pattern. If, for whatever reason, you need sequential access to every expression in the interpreter expression tree, then you can combine the interpreter pattern with the iterator pattern to make this possible. If you need to create specific iterators, depending on external or runtime circumstances, then you can combine the iterator pattern with the factory method pattern to create the correct type of iterator in the getEnumerator method. You can also use the memento pattern in combination with the iterator pattern. An iterator can use a memento to capture the state of an iteration. The iterator stores the memento internally. Okay, so here is a summary of what we have learned. The iterator pattern provides sequential access to the elements of a collection without exposing its underlying representation. The iterator pattern is pervasive in the .NET framework, but iterators are called enumerators. The IEnumerable interface acts as the aggregate base class, and the IEnumerator interface acts as the abstract iterator class. The .NET framework uses a compact iterator interface with only two members, current and move next. You can combine the pattern with the interpreter or composite pattern to provide sequential access to expressions and composites. You can combine the pattern with the factory method pattern to create custom iterators depending on external or runtime information.